talks session in general relativity. So the first speaker is David Fajman from the University of Vienna in Austria, and he will speak on the Einstein flow in 2+1 dimensions. And as far as I understand, he sent a video, so there will be no chance to ask questions, but we'll watch the video.
I would like to thank the organizers for giving me the opportunity to contribute to this session. I'll be speaking about the Einstein flow in 2+1 dimensions, and I'll start with this picture, cosmic microwave background, which tells us that the universe looks quite homogeneous and isotropic from our perspective, and we would like to understand whether Einstein equations can contribute to an explanation of why that is the case. So I'll be speaking about the Einstein equations in 2+1 dimensions, today introduce the formalism and present the result, and maybe I have some time for the proof. If not, I'll just mention briefly what the ideas are. So the Cauchy problem for the Einstein equations with large data, most of the results that we know about the Einstein equations concern small data, which means small in the sense of being close to a solution that we understand explicitly. Now we want to understand what can Einstein equations tell us about the evolution of any initial data, not necessarily close to any solution we know. So the standard way of obtaining the Einstein flow, which is simply just a family of metrics which explains us how the universe evolves in time, goes the following way. We take the Einstein equations for a space-time of this form, R cross M. M is the spatial manifold. We make a so-called ADM ansatz for the space-time metric G bar in terms of lapse, shift, and the spatial metric. And then we solve the Einstein equations, and the solution of the Einstein equations in particular contains this family of metrics GAB of T, and this is what I call the Einstein flow. So it tells us what how the universe is evolving in time, or our specific model in that case. There are various solutions to this problem depending on what initial data we start with, what the topology of this manifold M has, and the standard cosmological models. They know this trichotomy, so standard cosmological models look like this. So we have Gaussian coordinates, shift 0 and lapse being equal to 1, and then the spatial metric is some fixed metric times a scale factor, and the scale factor can go from 0 again back to 0, being a recollapsing universe, or it can expand for all time in case that the spatial manifold is a hyperbolic metric. So the recollapse is in case of a positive curvature, expansion is case of negative curvature, and if we have vanishing curvature of our compact spatial manifold, consider compact manifolds in cosmology, then the evolution depends on the matter content, so it's somewhere in between. These are some models to remind you of what may be possible in general, but these are all homogeneous models. We start with homogeneous data. The data stays homogeneous for all time. Here's the set of Einstein equations. We have the constraint equations that our initial data needs to fulfill. We have the evolution equations, and we know we need to impose additional coordinate conditions, fix our gauge freedom to obtain a well-posed system of equations that we can solve, and then we can analyze the solution. One example would be Gaussian coordinates. There are various others. Now, what are the questions for this system? What questions do we have? The ultimate question would be, we start with some initial data, G0, K0, and we solve the system. We obtain a solution, G of t, K of t, and we would like to know what this solution is doing. Ideally, for any initial data we can consider. So questions would be, does the flow exist globally in time? If not, then what singularities form? And if it exists global in time, what is the asymptotic behavior? Does it maybe converge to a uniform attractor? That would be interesting. This is this last question here. And answering these questions is possible so far only in the case of so-called small data. small initial data, which means that we are close to some homogeneous solution. Yeah, if I now, for the sake of this argument, also include non-cosmological spacetimes, for instance, Minkowski space, we know it is stable. That will be an example where we know what happens for small data, but we don't know what happens for generic initial data. So I mentioned here a few results of these case of small data. So we know Minkowski stability, we know that the Milne model is stable, that's a cosmological solution. We know that de Sitter is stable in various de Sitter-like solutions. That's the case of positive cosmological constant and cosmology. But all these results concern the small data regime. We know a few statements also for so-called large data, but in that case we always have additional symmetries imposed. So this is kind of cheating. I would really like to understand what happens for really generic initial data with no symmetry reductions or small data assumptions. So in general, we know that unique attractors cannot exist because we know that black holes can form, and for instance for Minkowski space, which, as I said, is not really a cosmological solution, but it's sort of similar. It still fits in this general discussion. We know that for large data, black holes do form, so there cannot be a unique attractor. There may be a family of attractors, of course, but then it depends really on the data that we start with, what happens toward when time goes to infinity. And for the cosmological solutions, for instance, if we take the Milne spacetime and we take some initial data for the Milne spacetime, then, or for de Sitter for that matter, then if we perturb this initial data strongly, so we go to some large perturbations, we don't know what happens. And it may be, of course, possible that we still converge back to the Milne solution if t goes to infinity, but we don't know that yet, and at the moment we have no idea on how to approach this problem. So I would say that this problem is completely open in 3+1 dimensions. So interestingly, in 2+1 dimensions, things are a bit simpler. Maybe that can be expected because 2+1 dimensional gravity is simpler in the following sense, that it is more restricted. Naively, I could say not so many things are possible to happen, so we have less degrees of freedom, so spatial curvature in that case would be determined fully by the scalar curvature, and the spatial topology is already fully determined by the genus, and the space of TT tensors, which is the, roughly speaking, space of gravitational degrees of freedom is finite dimensional. So we have a few simplifications. We also have things that make studying evolution problems more difficult, which is that due to the low dimension, perturbations decay slower. And also we have an interesting connection to higher dimensional gravity, like 3+1 and higher, through Kaluza-Klein reduction. If we impose some symmetry, U1 symmetry, for instance, on a 3+1 dimensional spacetime, then we end up with 2+1 dimensional gravity plus a scalar field. So 2+1 dimensional gravity has some implications for 3+1 dimensions. The study of 2+1 dimensional gravity has essentially been started by Vince Moncrief, who laid various fundamental foundations in this field and also resolved various problems. Most importantly, for what I will discuss, is joint work with Anderson and Tromba in '97, where they analyzed the asymptotic, some sort of the future behavior of certain models in that case, not the full asymptotic behavior, which I will come to in a minute. But this work has been quite important for what we will discuss in the following. So what is the result that I present? It is this theorem. So what this theorem says is the following. We take initial data, G0, K0, on a higher genus surface. Genus of M is bigger or equal to 2, so this is a closed 2 surface without boundary with at least 2 holes. and we take initial data such that we have a positive cosmological constant. And this space-time that evolves from this initial data, its maximal future development, has a CMC foliation. And on that CMC foliation, we have the induced data, G tau and K tau. And G tau is our Einstein flow. And what this Einstein flow does is it will, towards the future, asymptotically look like this spatial part here. So this is a exponentially expanding space-time with a spatial geometry, a rescaled spatial geometry, right? We have a time factor, this is our scale factor here. And here we have a fixed metric, sigma infinity, and this sigma infinity is a constant curvature metric on the surface M. And asymptotically, our Einstein flow G tau will exactly look like this. So this is what we state here. If I rescale my G tau with this time function, you can believe me that this time function is the inverse of this here. So this cancels essentially this factor. So if I rescale this metric to a more or less constant metric in time, so no expansion, then it will converge towards a target metric which has constant spatial curvature. So the important thing about this theorem is that this initial data here is completely arbitrary on that surface. There are no restrictions whatsoever. I take any initial data as large as you want on this surface. Under the Einstein flow, it will evolve to a constant curvature metric. So this universe completely homogenizes over time. Yeah, this space-time here is homogeneous, and this is what all these universes converge to. So completely irrelevant what the conditions shortly after the Big Bang were. Towards the future, all these universes look the same. So here, the Einstein flow, without any artificial ingredients of whatever inflation or what you may think of, leads to a homogeneous universe when you wait long enough. So a few remarks about this result. As I said, any initial data leads to this homogenization, and in particular, of course, the large initial data does so, which is what we find interesting here, or what I find interesting. And from a physical point of view, it tells us that lambda gravity in this case fully explains why the universe looks homogeneous for late times. And then there's an interesting complementary result to the one here by Creminelli et al., also from last year, where they make some assumptions on the space-time, but they use the mean curvature flow to evolve the slice in space-time, the spatial slice in space-time, and they get the same result even with matter content, but they make some a priori assumptions on the space-time. Okay, so a few remarks about the proof. There's not much time left, but at least I want to mention a few things on why this actually holds. So the interesting thing is that we take the important ingredient is that we take a constant mean curvature slicing of space-time, and we use Teichmüller theory to gauge our freedom in the spatial metric. So I have no time to really explain this, but after these two technical setups that are have both been invented by Moncrief et al., we end up at this reduced system of Einstein equations. And so this system essentially contains two elliptic equations, one semi-linear elliptic equation here for the conformal factor, which is essentially the spatial variation that remains that we need to control, that shows us that everything becomes homogeneous, and an evolution equation for the freedom in the metric, which is here encoded in these Teichmüller parameters, which are the degrees of freedom that the metric has in this gauge. and we apply essentially just standard methods to the system, namely some interesting sub and super solution method here for this conformal factor, and here just simple ODE techniques, and then we just plug everything together, all our a priori estimates, and at the end of the day we end up here with a long list of estimates where on the right hand side we have always decaying factors, and all these decaying factors show us that everything over time becomes homogeneous, and at no point in this argument we need to invoke any small data assumption. That is mainly the key result here in this proof. Okay, so I thank you for your attention, and for questions I would be very happy to receive questions via email, and so thanks a lot for your time and attention.
Thank you very much. Okay, so we go to the second talk, which will be by Gabriele Benomio from Princeton University, and the title of his talk is A New Instability for Higher Dimensional Black Holes.
Okay, can you hear me okay?
Yes.
Okay, let me okay, so I'd like to start by thanking the organizers for giving me the opportunity to speak. So the title of my talk is A New Instability for Higher Dimensional Black Holes. So my talk will consider solutions to the vacuum Einstein equations 3G equal to 0 with 0 cosmological constant, and we'll be looking at solutions Ng with dimension greater or equal than 3+1. So we won't restrict to the usual 3+1 dimensional setting, but we're also interested in higher dimensional solutions. So as we saw in other talks already, general relativity can be formulated as an initial value problem for quasi-linear wave equations in the Lorentzian metric G, which has a schematic form that you see here. So you have a quasi-linear structure. Sorry. I have a warning on my. Can you see me? Maybe you cannot see me. Start my video. Okay. Now you can see me, I guess. Okay. So a quasi-linear system of quasi-linear wave equations with the structure that you see here. So left-hand side, a quasi-linear structure of the system. Right-hand side, you have quadratic nonlinearities and first derivatives of the metric. This initial value problem has been proven to be locally well posed. So the initial value formulation and its of general relativity and this well posedness is fundamental because it gives the mathematical framework to study the dynamics of solutions to the Einstein vacuum equations, and in particular their asymptotic stability. In this talk, we've been interested in trying to understand the stability properties of solutions to the higher dimensional vacuum Einstein equations. But before moving to that, let me briefly recall what's the state of the art for the stability problem in the usual 3+1 dimensional setting. So nonlinear stability of Minkowski space has been proven in the monumental work of Christoph Kehle and remains a very active area of research in mathematical GR, while the nonlinear stability of sub-extremal core exteriors remains as a mathematical conjecture still open, and there has been a lot of recent progress on both the linear and nonlinear stability problem. Let me maybe briefly mention the recent breakthrough of the Fermosov, Zeger, Rodiansky, and Taylor that proves the nonlinear stability of such black holes without any symmetry assumptions. So this is the first nonlinear stability result for black holes without symmetry assumptions in the case of zero cosmological constant. So as we know, the curve stability conjecture sits within a more general conjecture, if you want, called the finite state conjecture. It also claims that the curve family of black holes describes all stationary asymptotically fat black holes in 4 dimensions, and thus characterizes all the possible stationary end states of black hole dynamics. So let's now move to higher dimensional general relativity. So higher dimensional GR is very interesting both from the physical and mathematical perspective. In particular, from the pure mathematical perspective, we are interested in trying to understand whether dynamical properties of solutions to the Einstein equations depends on the number of dimensions that one considers. And this is indeed the case, and it turns out that the dynamics in higher dimensions is richer than the usual 3+1 dimensional case. And most of the new features, the one observed in higher dimensions, already show up in 4+1 dimensions. So just one dimension higher than the usual 3+1 dimensional setting. So these two listed here are the two features that I think are most interesting of high dimensional GR, and they differ from the 3+1 dimensional setting. So the first is the failure of rigidity. So in 5 dimensions, there exist multiple explicit families of stationary asymptotically flat black hole solutions. They are independent one from the other. Here are some examples. So one example is a higher dimensional version of Schwarzschild black holes and a higher dimensional generalization of curved black holes that are known as Myers-Perry black holes. So these black holes are spherical black holes, and they, as I said, they have a strict analog in 3+1 dimensions. On the other end, there exist completely new families of black holes that have no analog in 3+1 dimensions and should be seen as completely independent from these families that you see here. One instance of these new families is black rings. From the dynamical point of view, the striking feature of some of these new families is that they're expected to be dynamically unstable to gravitational perturbations. As again, a prototypical example of this new instabilities in higher dimensions affects this family of black ring spacetimes. And these are the spacetimes that we'll be focusing on for the rest of the talk. So for this reason, I'd like to give you maybe some of the main features of these spacetimes. So black rings were first discovered in this paper by Imparani and Yar from 2002. And later on, more elaborated and sophisticated versions of this spacetime were discovered. But for the rest of the talk, when I refer to black rings, I really refer to the black ring matrix that are contained in this paper. So black rings are the first example of stationary asymptotically flat solutions to the vacuum Einstein equations with event horizon with event horizon of non-spherical topology. So the section of the horizon, meaning the 3-dimensional Riemannian manifold, the one obtains by intersecting the event horizon with a Cauchy hypersurface, has topology S1 times S2. And as I said, this has no analog in 3+1 dimension because all black holes need to have spherical topology, and marks a failure of rigidity within 5-dimensional black holes precisely because of the existence of this family here. There are spherical black holes. Okay. So these are two parameter family of explicit solutions to the vacuum Einstein equations, and can be described by these two geometric parameters, R naught and capital R, satisfying this relation that you see here. So capital R can be thought as the radius of the S1, and R naught as the radius of the S2 at the event horizon. So depending on the values of these two geometric parameters, one can divide the black ring family in two informal subfamilies. So one is the family of thin black rings when the parameter capital R is much larger than R naught. And one is the family of fat black rings when R naught is roughly comparable size to capital R. So remember, these are families of rotating black holes, but it turns out that the angular momentum of these black holes is fixed once these two geometric parameters are chosen. So, and this is the reason why, for instance, thin black rings are also automatically slowly rotating black rings. Okay. So from the dynamical point of view, the fundamental fact is that all black rings are dynamically unstable to gravitational perturbations. And these instabilities have been shown in a remarkable series of heuristic and numerical works. So some of the contributions are listed here. So depending on which black ring you select within the black ring family, the instability will have some slightly different features. But all the known instabilities that have been found in these works are linear and generally gravitational phenomena, meaning that they rise at the level of linearized gravitational perturbations around black ring spacetimes. And one example of these known instabilities for black rings is the well-known Gregory-Laflamme mechanism, the Gregory-Laflamme instability, which is an instability about existence. So it arises from the existence of an exponentially growing mode solution to the linearized Einstein vacuum equations around the black ring. So the aim of my research in my PhD was to try to prove a first mathematical theorem that complements this series of works and is suggestive of the dynamical instability for black rings. So to fully appreciate the mathematical content of the theorem that I ended up proving, I need to present one slide intermezzo about the role of the scalar linear wave equations in the analysis of the Einstein vacuum. So remember I told you that the Einstein vacuum equations can be understood as a system of quasi-linear wave equations. So simplest model for the Einstein vacuum equation is that of a scalar linear wave equation, now on a fixed solutions whose nonlinear stability we are interested in. And this fixed solution can typically be a black hole solution, and for us will be a black ring. So for nonlinear purposes, one typically studies uniform boundedness and quantitative uniform decay in time for the energy of solutions to the wave equation. And it is fundamental that these statements are uniform both in time and relative to solutions to the wave equation that one considers. And in the case of decay, we're not just interested in establishing decay, but we're interested in improving quantitative statements, meaning that we are interested in decay rates. And as is the case for many PDEs, in order to prove nonlinear stability results for the Einstein equation, sufficiently fast uniform decay at the linear level is necessary. Okay. So I'm now ready to state the main theorem of the talk that lies within the context, if you want, of linear waves on black rings. So the statement is the following. So uniform energy decay faster than logarithmic cannot possibly hold for sufficiently regular solutions to the wave equation on a very thin black ring. Okay. So the emphasis in the statement should be put on the word logarithmic, and I'll comment on this in a second. But let me point out that the theorem interests a restricted class of black rings, namely those thin black rings that I mentioned before. Okay, now back to the word logarithmic. So logarithmic decay is regarded as low decay because one expects the logarithmic decay at the linear level is not enough to prove stability results for nonlinear perturbations. And thus this logarithmic lower bound that my theorem claims is suggestive of a nonlinear instability for this class of black rings. So this result that I prove should be perhaps contrast with the polynomial decay for solutions to the wave equation proved by Lafermos, Rodiansky, and Shapetor-Rothman for the whole family of subextremal curved black holes. So this result here of Lafermos, Rodiansky, Shapetor-Rothman in particular allows to prove stability results for nonlinear scalar perturbations, and ultimately motivates the expectation that the curve family is stable for the full nonlinear problem. So as a solution to the full Einstein vacuum equations. So if you want another way to read my result, is that an analogous result to that of the Lafermos, Rodiansky, and Shapetor-Rothman cannot be proven. So polynomial decay cannot be proven for the whole family of black rings. Okay, namely because of this logarithmic lower bound. Okay, so this instability that my theorem suggests is a completely new phenomenon that has nothing in principle to do with the non-instabilities that were observed before in the series of works that I mentioned. So let me stress again that a novel element here is that for the first time in the case of black rings instabilities, this instability is supported by mathematical theorem. It is a nonlinear instability associated to slow decay of linear perturbations, as I explained. And this contrasts with the instability previously known for black rings, which were linear instabilities, okay? And this instability should be expected to be already manifest at the level of nonlinear scalar perturbations, meaning where one studies, for instance, a quasi-linear scalar wave equation of this form on a fixed black ring background with a quadratic nonlinearity in first derivatives of the solution on the right-hand side, which resembles the structure of the Einstein vacuum equation that I showed you at the beginning of the talk. So this can be contrast, for instance, to some results on curved black holes, where small data global existence for solutions to equations of this form can be proven. Like, for instance, there's a very relevant, interesting work by Luke in this direction. And should also be contrast to the previously known instability for black rings, which were genuinely gravitational phenomena. So they were relying, if you want, on the tensorial structure of the Einstein equation. Last feature is that this instability can be ascribed to a precise geometric property of very thin black rings, which is known as stable geodesic trapping. So geodesic trapping is a phenomenon that we are familiar with in general relativity, and it has to do with the existence of null geodesic, which for all values of their affine parameter will remain in a bounded region away from the event horizon and infinity. So if by perturbing ever so slightly the initial position or velocity of a trapped geodesic, the geodesic that one obtains doesn't intersect neither the event horizon or null infinity, then we say the geodesic trapping is stable. Otherwise, we say the trapping is unstable. And the appearance of stable null geodesic trapping in black rings is really a fundamental geometric feature of these spacetimes. Let me point out that for stationary asymptotically flat solutions to the Einstein vacuum equation, this is a novel and perhaps surprising feature of high-dimensional general relativity. So stable geodesic trapping doesn't occur, for instance, in curved black holes. But one can have geodesic trapping, but geodesic trapping is always unstable. Okay. So trapping is a geometric property of the manifold that interacts with high-frequency components of solutions to the wave equation. So in the regime of Diophantine approximation, one should think of high-frequency waves that's traveling in the proximity of null geodesics for a very long time. And this should be seen as an obstruction to dispersion. So now it turns out that even in the presence of trapping, one is able to prove decay for solutions to the wave equation, but the nature of trapping is a crucial indication of how fast the uniform decay rate can possibly be. So with the nature of trapping, I do mean whether trapping is unstable or stable. So stable trapping, if compared to unstable trapping, is from the dispersive point of view way worse, and it forces weaker dispersion of waves. So this weaker dispersion is what ultimately forces the slow, meaning only logarithmic decay of linear scalar waves in the case of black rings. Okay. So since this instability can be ascribed to a precise geometric property of thin black rings, it is reasonable to expect that this instability mechanism is in a sense robust and may affect more general spacetime which exhibit stable trapping. And this is the observation that I have in this slide here. So in fact, stable trapping appears in other higher dimensional stationary asymptotically flat black holes, which should also for this reason be expected to suffer from the same type of instability. And more generally, all stationary solutions to the Einstein vacuum equations which admit stable trapping may be conjectured to be nonlinear as stable as solutions to the Einstein vacuum equations. And this feature as well can be contrasted to the previously known instabilities for black rings, like for instance, the Gravitational instability, which is a mode instability, and in a sense relies in a more delicate fashion on the structure and algebraic form of the black ring metric. While this instability mechanism here should be expected to be more robust in general. Okay. Let me maybe say a couple of words about the strategy of the proof. So the strategy is to try to capture this stable geodesic trapping property, so a geometric property of the manifold via some analytical construction. And what we do is to construct a sequence of 10 periodic approximate solutions to the wave equation, which are usually known as quasimodes, which are very much localized around stably trapped null geodesics. So proving the existence of these quasimodes with a suitably small error fundamentally relies on the presence of stable trapping. And it is in fact the hardest, if you want, more challenging part of the proof. So in the proof that I present in my paper relies on some ideas that were previously developed by Ozegeles Mulevici in a different context, namely in the context of ADS black holes, and combines this idea with some new techniques, like for instance being able to deal with a wave equation that is not fully separable. So on black rings, one cannot fully separate the wave equation, and this introduces new difficulties in the proof of this result. Okay, I think that's everything that I wanted to say. Thanks for listening.
Yeah, thank you very much. Are there any questions from the audience? Yes, please.
The logarithmic decay, is this like in any gauge? Or is it this statement in a fixed gauge, or you say that this statement is for any gauge?
Sorry, I missed the start of the question. You're referring to my theorem, and you're asking a question about gauge. Did I understand correctly?
Yes.
Okay. So my result is really for the scalar linear wave equation. So you should think of having a fixed black ring spacetime, and then you study the wave equation on that fixed
Okay.
on that fixed background, okay?
Thank you.
So there's no, So that's not, I mean, gauge is not dynamic. Gauge is not dynamic. So the background is fixed, and you study wave equation on that background.
Yeah. Okay. Sorry. Then I misunderstood. Thanks.
Okay, any other questions? Online, any questions?
No, not so far.
Okay, then in view of the time, let's go to the next. Let's first thank Gabriele again. Thank you for your talk. And the next talk is by Nikolaos Athanasiou from Imperial College London. And the title is The Scale Critical Trapped Surface Formation Criterion for the Einstein-Maxwell System. Please.
Thank you very much. Can everybody hear me? Yeah. All right. Hello from me to everyone. I would like to begin by thanking the organizers for giving me the opportunity to speak at this conference. And I would also like to mention that everything I'm going to talk about is based on joint work with Xinliang An, who is a co-panelist today. Okay, so the outline of my talk will be as follows. I will skim through an introduction to the problem. I will then discuss the setup in which our theorems are formulated. And I will close with the actual argument of formation of trapped surfaces. All right. So our story begins on November the 25th, 1915, when Albert Einstein presents his field equations of general relativity to the Prussian Academy of Sciences. And according to this theory, a space-time is a four-dimensional manifold M equipped with a Lorentzian metric G, satisfying the Einstein field equations as seen below, where the right-hand side of this equation is some given stress energy momentum tensor. R mu is the Ricci curvature tensor, R is the scalar curvature, and the right-hand side is prescribed. So this was very revolutionary because it showed the idea that gravity is essentially a feature of geometry of the space-time. Okay, so in early years, research was basically following two broad directions. Okay, so the first work was work towards experimental verification of the theory. So make sure that whatever Einstein is saying can be seen somehow in the real world, and hence that there is physical basis for the theory. And the second, more closely related to our talk, is work towards identifying explicit solutions to the Einstein equation. And this didn't take long to happen, like at least for the first solution. So the first non-trivial solution to the vacuum equations was given by Karl Schwarzschild in a letter to Einstein only a few months afterwards. I think it was December 1950, in which he gave us the well-known Schwarzschild solution. But people did not necessarily understand Schwarzschild immediately and what it encompassed. So it was only understood by Lemaitre in 1932 that the metric, the Schwarzschild metric, contains a non-empty region B with the following features. So any observer inside this region B cannot send a signal to an ideal conformal boundary at infinity, the future null infinity, and in particular, every time-like or null geodesic that enters the interior of B is future incomplete. So as soon as physicists and mathematicians saw these features, they were hoping to be able to associate to them the notion of a pathology or an accident existent only due to the high degree of symmetry already imposed in the solution, and that in generic solutions, whatever that meant, the notion of an initial value problem for the Einstein equations had not been developed yet, but in generic solutions to those equations, such bad phenomena like this region B would not arise. And this is where Sir Roger Penrose does a remarkable contribution, okay? So one for which he was awarded the 2020 Nobel Prize in Physics. So he shows that black hole formation is a robust prediction of the general theory of relativity. And he does that by introducing the pivotal notion of a trapped surface. So given a general four-dimensional time-oriented Lorentzian manifold, and a closed space-like 2 surface, we may define the 2 standard well-known second fundamental forms chi and chi hat, okay, that correspond to, so the trace chi and trace chi hat would correspond to the infinitesimal change of the area of the sphere along the future directions. So if both trace chi and trace chi bar are negative, then the surface is called trapped. And what this intuitively means is that along every future direction, infinitesimally, the area of the sphere tends to decrease. The remarkable contribution now, so what do we do with this trapped surface? Well, Penrose's incompleteness theorem shows us the following. So if Mg is a globally hyperbolic spacetime with a non-compact Cauchy hypersurface, and you satisfy a very good, very physical assumption, okay? So R v comma v is greater or equal to 0 for all null vectors v. The vacuum equations satisfy that identically. So if M contains a closed trapped surface, then M is future causally geodesically incomplete. And as I'm sure all of you know, this doesn't tell you the type of singularity that exists. Singularity exists indirectly as geodesic incompleteness. But as is usual in research, the settling or the handling of one question immediately gives rise to many, many more. Okay. So a natural question that didn't take long to be posed was whether, because at that time, the only way to guarantee the existence of a trapped surface in the spacetime was to assume one in the initial data. But the question is, can trapped surfaces form in evolution from untrapped initial data? Is there a configuration where I'm untrapped and in the future I become trapped? So the history of this question is rich and is ongoing. Okay. So I believe it was first given to Christodoulou by his supervisor in the complete absence of symmetry, and I think that Christodoulou has said that he was unable to do it and he changed the topic just so he could get his PhD. But later on, we will see that he proved it many, many years later in 2008. But so we start by a series of papers by Christodoulou for the gravitational collapse of a scalar field, in a series of papers where he understands completely the entire picture of gravitational collapse in the case of spherical symmetry for the scalar field, which is the simplest toy model you can assume for the Einstein equations in spherical symmetry. And then the real breakthrough came in 2008 in the absence of symmetry for the vacuum equations, in which a new idea was developed. Okay, so this was termed delta short pulse method. So due to the stability of Minkowski spacetime result, we knew that somehow, if we want to see pathologies occur, like trapped surfaces, we would need our data to somehow be large. But if we were too large or uncontrollably large, we wouldn't be able to prove existence of a spacetime long enough for a surface to be able to form. So what Christodoulou did was manage to give an ingenious answer of initial data that somehow gets propagated along through the Einstein equations. And he managed to show existence of the spacetime for long enough for a trapped surface to form. So immediately afterwards, we have the work of Kleinerman-Rodniansky on trapped surface formation using a different scaling. And an important aspect of this work is that it reduces a 600-page work to 100 pages, and hence everything becomes much more manageable. There are other technical simplifications, like involving the number of derivatives required, and the extensions of PIN-U for Einstein-Maxwell. So then we have another interesting question, which is, an important work in this area, which is the work of An and Xinliang An and Jonathan Luke on a scale critical trapped surface formation criterion in a finite region. And this basically asks the question, how large do my data need to be? What is the minimum largeness required if you want to obtain trapped surface formation? Then we have the works of An in 2018 for apparent horizon formation, and the work which served as the basis for our joint work with Xinliang, which was the scale critical formation criterion for the vacuum equations. All right, let's go to the mathematical setup of our theorem. As is usual in this large data problem regime, the space-time we construct is covered by a double null foliation given by the three-dimensional incoming null hypersurfaces H bar U bar. U bar is between 0 and 1, not between 0 and delta, as is the usual Christoph Kehle ansatz. Okay? And outgoing null hypersurfaces, U infinity less or equal than U less or equal than some A that we're going to prescribe. Okay, so minus A over 4. And their pairwise intersections S U bar. So in this double null foliation with the frame given, we will construct and talk about the Einstein equations. So in collaboration with Xinliang from NUS, we have looked at the Einstein-Maxwell system. So now the right-hand side corresponds to electromagnetic radiation. And our results can be summarized in 3 theorems. Okay, the first one is a semi-global existence result. And it goes as follows. So given I0, there exists a sufficiently large A0, depending on the initial data, such that the following holds. For any A greater than this value, and with smooth initial data in the characteristic initial value problem, which is chi hat and alpha f being the null Maxwell component, corresponding to the free data for the Maxwell equations. So AF, A is F for A. Satisfying the following ansatz here along U equals U infinity, so along here. And here we prescribe Minkowski data. Then, with these ansatz, the Einstein-Maxwell equations admit a unique smooth solution in the region U infinity less or equal than U less or equal minus A over 4 and U bar between 0 and 1. Okay. The largeness in the data can already be seen if you think that A can be large. So the second one steps directly on the first one, and this is a formation of trapped surface statement. So if I have my initial ansatz, and moreover, I assume that along U equals U infinity, along every direction, this integral is greater or equal than A, then we have a trapped surface at the corner of the space-time, which would be here. All right. And let me just point out, even though it hasn't been written down explicitly, that we fully expect to be able to loosen this assumption purely on the grounds of the work of Kleinerman, Luke, and Jordanowski, who give an anisotropic criterion for trapped surface formation. And the third one is the rescaling of theorem 3 and constitutes a scaling critical trapped surface formation criterion for the Einstein-Maxwell equations. So by a rescaling of the coordinates, essentially, we can reduce our estimates to a region of size 1 to a region of size delta and obtain the corresponding estimates for all the Ricci coefficients, curvature components, etc. And we see that they're very, very close to, very similar to An, Luke. And that's where we can talk about scaling critical. So the setup of the problem already suggests certain difficulties. One is that, okay, we have now an inhomogeneous part in the Bianchi equations here, so the Bianchi equations contain a collection of terms that are not present in the vacuum equations, and these terms cannot always be estimated through the null Maxwell equations. So you can look at this example, okay? So this term here on the right-hand side would contain the term rho f, sigma f times nabla 4 alpha f, where these are the components of the given Maxwell tensor. But if you look at the null Maxwell equations expressed in the double null foliation, there is no Maxwell equation, there's no equation for nabla 4 alpha f. So we overcome this issue by introducing very normalized components. Beta tilde alpha is beta alpha minus a half R for A, somehow killing this bad term. And beta bar tilde, and then we rewrite all the Bianchi equations in terms of beta tilde and beta bar tilde. And the second difficulty is that the Maxwell equations need to be handled on one level of differentiability higher than the curvature components, and we introduce elliptic estimates to overcome this. The scale invariant norms and the structure of the proof now. We introduce, for time I will be a bit fast because I see that I'm running over time. Okay, so essentially we introduce a systematic way of introducing the norms that will be used in the proof, this bootstrap argument proof that we're going to describe. So we assign a number called signature for decay rates to it, first introduced by An. So for every time in the definition of a tensor field we have EJ, we call it NJ of phi. So I award its appearance of E4 by 0 points, its appearance of EA by a half, and its appearance of E3 by 1. And for such phi, we define the corresponding norms, the scale invariant norms. Okay? And it is in these norms that we're going to be tackling the entire proof. Here I have an explicit construction of how the norms go. And I don't want to stand on those, but what I do want to explain is the following. There is a conservation and balance of signatures along every transport constraint Bianchi and Maxwell equation. Okay, so the way we prescribe it is consistent throughout the Einstein equations expressed in W. And the point is that the signature for decay rates allows one to give norms such that in the evolution of these large data, most of these quantities, these norms, are bounded by 1, okay, with the exception of a few anomalous terms, thus giving us a way to propagate and control. And the third point, which is very crucial, is that the Holter inequality expressed in scale invariant modes allows for a smallness factor to appear, okay? So the two-scaled norm of phi1 times phi2, that the nonlinear terms, is less or equal than 1 over u times the L infinity norm times the L2 norm, okay? And there's a corresponding thing for L1. The point being that if u is large, 1 over u is a smallness factor, okay? And this is crucially used in all the bootstrap arguments that we prescribed. And you can contrast this to Kleiner-Marodiansky's norms. And finally, the proof of semi-global existence rests on the following standard sequence of estimates. So the rich norms are bounded by initial data plus the curvature norms plus the Maxwell norms. Then we close with elliptic estimates. And then we close with the energy estimates for Maxwell components F and the energy estimates for curvature R. And based on those estimates, a standard procedure can be invoked to provide the proof of semi-global existence. I don't think I have time to explain the trapped surface formation argument once you assume the extra condition that I have.
Yeah, maybe you can wrap up because we're running out of time.
Exactly. Yeah. So I can stop here. This was the idea of the proof here. Okay. So yeah, with that I thank you for your attention. The point being that the formation is just an OD argument after the existence has been tackled. Thank you very much.
Yeah, thank you very much for your talk. In view of the time, maybe one quick question, if there's a quick question. Otherwise, we're moving to the next talk. So thank you again, Nikos, for your talk.
Thank you.
So the fourth talk of today is going to be by Xinliang An from the National University of Singapore, and the title is Anisotropic Dynamical Horizons Arising in Gravitational Collapse.
Okay, yeah, so give me one moment to share the screen, yeah. Okay, so can you hear me? Okay, so I would like to thank the organizers for the invitation. Also thanks Nikos for the previous talk. So yeah, for today I will talk about anisotropic dynamical horizons arising in gravitational collapse. These are some other of my recent work with Diane Gajic, Qing Han, and Ruixiang Zhang. Okay, so in the below, so we will mainly focus on Einstein vacuum equations and Einstein scalar field system. Okay, Einstein real scalar field system. So in 1991, Crystallo proved a sharp trapped surface formation criterion for the Einstein scalar field system under spherical symmetry. So once a trapped surface is formed, so Crystallo further proved that the generic Penrose diagram of the spacetime of the gravitational collapse spacetime is as follows. So in this picture, so the A is apparent horizon, T is a trapped region, and the B is a space-like singularity. Okay, so yeah, so a natural question based on this picture is to ask, so how strong are the space-like singularities? So Crystallo considered part of this question in his paper. So if adapting a double non-foliation with omega and R, okay, so Crystallo employed an ODE type argument and obtained the lower bound. And this is via an algebraic calculation. And for each point in the trapped region, he showed that the lower bound would be 1 over R to the power of 6. Okay, so R is the area radius. Okay, and the following an extension principle established by him as well, it can be proved that for the Fajman scalar, the upper bound would be double exponential 1 over R. So here is we want to improve both estimates to the sharp rates. Okay, so the first one is a joint work with Ruixiang in 2019, which is for the same equation, Einstein scalar field system on spherical symmetry with the same initial data. At each point in the trapped region, we show that there exists a positive number n depending on initial data, such that the blow-up upper bound would be a polynomial, 1 over R to the power of n. So the other proof is non-perturbative. So a key step in this proof is to show that for the scalar field, which is quite singular, which is for the scalar field, for the derivative of the scalar field, partial u phi and the partial v phi, phi, and the blow-up rate would be exactly 1 over R to the power of 2. And the number n here will depend on the number, which is d1 tilde and d2 tilde. So the next question we want to ask is, can we calculate this n? And this is something we want to know. And for u and v in the trapped region, which is very close to the time like infinity, in a joint work with Gajic, we can calculate this n along the space-like singularity. So so in this work, we prescribe initial data, which is consistent with Price law along the event horizon and prescribed data along the H bar. So when this is quite close to the time like infinity, we show that for the Fajman scalar, the blow-up rate would be very close to 6. It will be 6 plus perturbation. And the perturbation is quite interesting. So this is the blow-up rate. This would be small. This would be some constant, and times v to the minus 2q, and this is v to the minus 2p. And we know that this if the point is moving along this direction, v goes to infinity. Okay, so this is very precise kind of calculation about the remainder term. So here is rho d1 and rho sigma are positive constants, and the rho here will depend on the method we use, only on m, and the sigma here is so this sigma depends on the initial data. And interestingly, this d1 is very interesting. So this d1 is precisely the constant, which is the lower bound for the Price law. So so this result actually linked the curvature block rates along the space-like singularity to the Price law along the event horizon. And since so for all the constant rho, sigma, and the d1 are positive, so we actually know that the lower bound 6 is not sharp, which is the lower bound of the Fajman scalar is strictly less than is strictly greater than 6 in this region. And when this cube move to the time like infinity, we have the v goes to infinity, and we can find that the difference between this number to 6 actually goes to 0, which means the blow-up rate will strictly go larger than 6. But when this point moving to time like infinity, the blow-up rate will converge to 6. So in particular, because we have both lower bound and upper bound, and in particular, if we choose a different way, the block rates along the space-like singularity are not limited to discrete finite choices, and this is a new PDE block phenomenon. Okay, so yeah, so this is for the spherical symmetric case. So what can we say about the below picture out of symmetry? So the story will date back to a breakthrough result of Crystallo in 2008. Because of the time limit, so let me first state a recent result by me and Qinghan. So so this is the anisotropic apparent horizon result, which is thank Nikos for the introduction of the setup, which is let Chi-hat to be the shared tensor. Okay, so we prove the following theorem, which is in this shadow region is the region we want to consider. We prescribe Minkowski data here, okay, and we set the Chi-hat, which is along here, to be bound less or equal to square root of a, okay, and the Chi-hat could be 0 in a lot of regions, and more precisely, we require the integration from 0 to u bar, and it's like a function times u bar times a, and this function is any function between 0 and 1. Okay, and we only require that this function to be non-zero at some point on S2. So yeah, so for a lot of angular directions, this function could be 0. And for this initial data, we can show that along each incoming non-hypersurface, there exists a unique modes. And under quite general conditions, along each incoming non-hypersurface, there would be a unique modes. And then we put all these modes together, and this will give us the apparent horizon. And the apparent horizon would be smooth if the initial data would be smooth. And under quite general conditions, we can also show that this would be a very anisotropic apparent horizon. And we can show that the apparent horizon would be space-like, hence a dynamical horizon. So and also furthermore, this is along each incoming non-hypersurface is corresponding to this picture, and so this two surface, which is in the dark green region, this is the anisotropic modes we constructed. So besides the results we just stated, and I will also give the first mathematical examples of anisotropic modes and anisotropic apparent horizon formed in dynamics, because we can show that it is really anisotropic, and we can calculate everything for this geometric shape. And so in general, that we construct the anisotropic modes with single and multi-valleys. The pictures we just showing here just demonstrate finger-shaped modes with 2 valleys. And we can have a mode of this one, but with many valleys. Okay, so and back to the history side. So back to 2008, so Crystallo proved the following breakthrough result. Which is we solve Einstein vacuum equation in this colored region with characteristic initial data such that we put Minkowski data here, and then Crystallo introduced a small parameter delta, and for the shared tensor with both upper and lower bound, which delta minus a half over u. Okay, Crystallo shows that at this point, which is 2 surface, is a trap surface of radius roughly 1. And after this result, and Kleneman, Luke, and Rodiansky gave a fully anisotropic trap surface formation criterion, which is they realized they relaxed the lower bound and showed that an anisotropic trap surface could form. And so later in my work with Jonathan, Luke, so we improved Crystallo's result to a scale critical result. And so we introduced another parameter a, which could be much less than delta minus 1, and this would be this is the first scale critical result for Einstein vacuum equation. And besides the extensions, there are quite a few works towards the simplified proof of trap surface formation by Kleneman, Rodiansky, by myself, so for my work in 2019, so I gave a simplified proof with 60 pages via the signature for decay rates, like Nikos just mentioned. And together with Nikos, we extended this result to the Einstein-Maxwell case. Okay, so so in 2017, so I tried to construct the apparent horizon. And so there is, so based on my work with Jonathan, so we have an estimate from the hyperbolic side. And furthermore, that if I require that the shared tensor around the initial data to be closed, so in a neighborhood of square root of A, okay? So more precisely, I require the integration here, which is like U bar times A with a function. But the function here, in that paper, I require to close, somehow close to 1, which is I require it to be 20 over 21 and 22 over 21. And under this kind of assumption, along each incoming non-hypersurface, I can show that there exists a unique modes, and except this point, which is a singular point, and the collection of modes will form a smooth apparent horizon. And furthermore, that if I required more restrictive conditions in that paper, which is I required this F to be very close to 1, and I can show that the apparent horizon would be space-like. So hence, both space-like and the smooth apparent horizon, this gives a dynamical horizon in physics literature. So mathematically, we are trying to do the following, which is fix each U bar. We have a incoming non-hypersurface. So we know, for example, this would be a trapped surface. This would be an untrapped surface. And we want to try to find the modes. And along the incoming non-hypersurface, the equation to find the location of the modes, which is try to find what would be this capital R. And this capital R will satisfy a new quasi-linear elliptic equation. So in my paper in 2017, so I found a new gradient estimate using this assumption, and find a new gradient estimate and try to solve this elliptic equation. And once the apparent horizon is proved to be space-like, and there is a quite interesting physics called related theorem could be proved, which is along the apparent horizon, and the area toward this direction would be increasing, and the area goes toward this direction will go to 0. So with no symmetry assumption, so the above result in 2017 is the first result showing that a dynamical horizon exists. And if we consider area as entropy, and this theorem is the corresponding the second law. So our results in so our very recent result, which is just stated with Xinliang, generalize this theorem to the general anisotropic scenarios, which is for the function here, we only require this to be larger or equal to 0, and require this function to be only non-zero at maybe several points, 1 or 2 points, and even several points. And the techniques we used are different, and especially for the elliptic part. And so in this new result, we use non-perturbative elliptic techniques such as Moses iteration and the Strong's maximal principle. Since I still have some time, maybe I mentioned a little bit about the details, which is, so this is the elliptic equation for the modes along the incoming non-hypersurface. If for this case, which is in my 2017 paper. So the crucial thing is I try to get the C1 estimate, and from L infinity, from the barrier to C1 to C1 alpha, C2 alpha, and to close everything. And there is I construct a function called the HR, which is the function, the coefficient of pickup to be consistent with the coefficient here. And if we put this into the Bochner formula, and interestingly, we found that the coefficient in front of both gradient R to the power of 4 and gradient R to the power of 2 to be positive. If we pick up HR to be 1, and the Bochner formula will give you a negative gradient R to the power of 4, and you cannot prove anything. And if this inequality is true, and because this is a low order term, not only we have gradient R is bounded, I also have gradient R is less or less than 1. This is the key to prove the previous result. But for the later result with Xinliang, so the analysis part would be much more involved, because so for there is we use the Moses iteration, which is we starting from the L infinity, we cannot go to C1 directly because the coefficient F could be 0 in a lot of places. We need to slowly from L infinity go to C0 alpha. And this we need to go through the details of Moses iteration to make sure that the whole, and also we need to use estimate in unlook to make sure that everything is can work out. And then later we improve the regularity step by step. And then we also use the invertibility of linear right operator where the positivity of first eigenvalue for quasi-linear problem, and the Theorem maximal principle is heavily used, and the space likeness of the planet horizon for the general case is proved via the elliptic estimate, and once we have the constant, which is for the f, at which point it would be non-zero, we can trace all the constant in the estimate. And I think I will end up here, and thank you.
Yeah, thank you very much for your talk.
Yeah, thanks. Yeah.
Maybe a quick question. We're already almost 15 minutes over time. If not, we thank Anne again and move to the next talk. Thank you very much.
Thank you. Thank you.
So the next talk is given by Jinzhao Wang from ETH, and the title is Local Gravitational Energy in Higher Dimensions.
So thank you very much for giving me this opportunity to present my work. I'm going to speak about the small sphere limits of quasi-local mass in high dimensions. So in general relativity, we know that purely gravitational energy cannot be covariantly represented as a density. So one has to make a compromise. Such a compromise is made in the program of quasi-local mass, which attempts to characterize the gravitational energy in a quasi-local manner. So mathematically, it's a functional that assigns a positive value to a codimension 2 topological sphere using the data associated with the sphere. There are many proposals started by Hawking and followed up by many physicists, and now this program is mainly carried over by mathematicians. It's a difficult problem because we wanted to satisfy a bunch of properties in order to call this a proper mass, and among which positivity, rigidity, monotonicity are all very important. And also we should expect this to behave in accordance with the masses we already have in general relativity, namely the global ADM mass or boundary mass at infinity, or locally you expect this to give you back the stress tensor. We should focus in this talk about the small sphere limit, which probes the local energy. So mathematically, how do we probe the local energy? So there's a canonical way proposed by Horowitz and Schmidt, known as Lycon cuts. So the way you do it is you say at the point of your interest, and you pick a time-like direction, and one can define a one-parameter family of spheres by simply cutting the Lycons according to the affine parameter. And then if you take this spheres down, shrink down to the point, and you evaluate your quasi-local mass functional on these surfaces, you should in the end obtain some limit. And in 4 dimensions, if the point sits in a place where there's matter around, you should expect this a good quasi-local mass proposal should give you back the stress tensor. And if it's in vacuum, you should get something called the Bell-Robinson tensor. So the Bell-Robinson tensor that sort of characterizes the energy in the vacuum, it's really sort of a square in the wire tensor. And it's a unique one that is a dominant, symmetric, and traces. In this limit, we are interested in this particular component, which is sort of the 0000 time component of this tensor. And it can be conveniently written in terms of the so-called electromagnetic decomposition of the Y tensor. And written in this form, this really resembles how energy is treated in electrodynamics. So we think of this Bell-Robinson tensor as being some sort of a characterization of gravitational energy in the local way, in the local limits. In high dimensions, this quantity actually have a unique generalization. If you assume it's still square in Y tensor and it's dominant, basically means it should be a positive definite. And then the expression for the time for 0000 component just looks like this, which is some electromagnetic decompositions of Y tensor in high dimensions. So we want to check whether the small sphere limits in high dimensions give us this expected behavior for various proposals of quasi-local mass. The immediate difficulty is that usually these proposals are only given in 4 dimensions. In order to make the calculation, we should attempt to extend the definitions to high dimensions. And we try to do that for the Hawking mass, the Brown-York mass, and the Liu-Yau mass. And we put sufficient assumptions so that in the end, we're not looking for a well-sound definition for this of these quantities in all cases, but they are at least sufficient for our small sphere limit calculation. So the first case we look at is the so-called Hawking mass, which is sort of one of the first definition or proposal of quasi-local mass. And this is just defined in terms of the geometric data you obtained, and in particular, say the Ricci scalar of the sphere and the null expansions, the mean curvatures of this surface. And in higher dimensions, you simply keep using the same formula, but instead of in 4-dimension case, you can get rid of the first term by Gauss-Bonnet. In higher dimensions, you should keep this Ricci scalar term. And this is well accepted formula of Hawking mass in high dimensions is also used in other studies about global asymptotics. And a good sanity check is that it reduced to the so-called Meissner-Sharp mass for round spheres. Okay, so if we take this as our definition of Hawking mass in high dimensions, we can make the calculation. And a confirmation of this being a good proposal is that in the non-vacuum small sphere limit, we do obtain back the stress tensor, and the coefficient in front of it is just the volume of the ball. So it's also the coefficient is also correct. However, in vacuum, we obtain a limit that is not the unique Bell-Robinson tensor we thought it should appear, but rather it's some other quantity W, where Q is the Bell-Robinson tensor, which is not equal to that. I will tell you what W is later. Okay, so now the main point is that it's something that is not the Bell-Robinson tensor, if you care about a vacuum case. Now let's look at the second proposal we study, which is the Brown-York mass. And the Brown-York mass it's a quasi-local mass that is constructed using entirely different methods than the Hawking mass. And you sort of obtain this from some Hamilton analysis of the gravitational action. So the formula looks like this. Basically, it's a integration of the mean curvature over the sphere. But as always in this kind of Hamiltonian problems, you have to choose a 0-point energy. And it's a standard to choose 0-point energy using the method of isometric embedding. Namely, you embed your surface into a flat reference space-time, and you demand this embedding to be isometric, so that you evaluate the same quantity in your reference space, and you subtract it from your energy functional. And so this defines for you the Brown-Young mass. A remark I should mention is that in this case, for this small sphere limit calculation, we just use the same embedding as used by these authors who studied the same problem in 4 dimensions, where you embed the surface into a light cone in a Minkowski space. Okay, so if we do that, we obtain, again, in the non-vacuum case, the stress tensor, and in the vacuum case, the same W tensor in all dimensions, which matches the result in the Hawking mass calculation. And so remember, these are very different quasi-local mass proposals, and nevertheless, we obtain the same limits. And without further details, I can just tell you that the small sphere limit of the Liouville mass is also characterized by this same quantity in the vacuum, and the stress tensor in the non-vacuum. So what is this W quantity? So in all dimensions, it is written using the so-called electromagnetic decomposition of the Y tensor as this formula here. Whereas the Brer-Robinson superenergy is written down here. So they are clearly different, but they do actually match in 4 dimensions. So one important point I should make is that notice that here the D squared term has a minus in front of it. So it depends on the details of your geometry at the point. This W can be not positive in general. So what have we learned? We learned that the Brer-Robinson superenergy, although it's a unique generalization across all dimensions, it does not characterize the small sphere limit of quasi-local masses in dimensions higher than 4. So in these general cases, we should use a different quantity that we discovered here, which I call W instead of Q. And this W quantity, unfortunately, is not always positive. So for future direction, I think it's worth to investigate more on the seemingly universal quantity, right? We see it from different proposals. We see the same quantity to clarify this physical meaning. However, I think it's more likely that it's just this definition we have in 4 dimensions. These proposals for quasi-local mass in 4 dimensions we have are simply not good enough to be generalized across all dimensions, except maybe the Barnick mass. Because this negativity of this quantity or non-positivity of this quantity sort of hints at there are some problems of using this 4-dimensional proposals to higher dimensions. So I think we really need some new proposals that works for all dimensions. And that's all I want to say. Thank you very much.
Thank you very much. Maybe quick question. Are there questions from the online audience?
No, I don't see any.
Okay. Okay, so thank you very much again.
Thank you.
And we'll move on to the next talk, which is on site, and by Christoph Kehle, and the title is Diophantine Approximation as Cosmic Censor for ADS Black Holes.
Yeah, thanks a lot for the opportunity to speak. Thanks to the organizers. So without further delay, let's jump right into a black hole. Okay, no, this was not the correct thing. Okay, thanks. Now it's correct. Let's jump right into a black hole, namely in the Kerr family of black holes, and that's a rotating black hole, and the solution of the Einstein vacuum equation for lambda equal to 0. We have heard loads of it through this conference, but particularly about the exterior region, which is here. My talk will concern the interior region, which is here. But let's talk about some features of Kerr first. So first, Kerr is incomplete if we actually also include the interior. Namely, an observer which is so courageous as to enter the interior will reach the future boundary of the Kerr black hole in a finite proper time. This future boundary has the property that the space-time is smoothly extendable beyond that boundary, but however those extensions are highly non-unique. So this means that an observer approaching that boundary will only experience finite tidal deformations. However, the fate of the observer is undetermined because there are infinitely many smooth extensions which are compatible with classical relativity. And that is a failure of, that is a well-known failure of global predictability of the theory. And if we also include now cosmological constants, let it positive or let it be negative, then a same phenomenon occurs, namely the interior is very similar. We again have this smooth Cauchy horizon, both in the negative Kerr case, in the Kerr ADS case, or in the Kerr de Sitter case. And beyond which, again, the solution is non-uniquely extendable in a smooth manner. And the good toy model, let me already mention it here, for the Kerr solution is the spherically symmetric Reiser-Nordström ADS or Reiser-Nordström DS solution of black holes to the Einstein-Maxwell system. Okay, so that's kind of the problem of smooth Cauchy horizons in general relativity. And however, of course, those Kerr metrics, they're highly explicit because they're in algebraic form, they're highly explicit solution, and one is always interested what is the generic behavior. So Penrose suggested a way out of this problem of smooth Cauchy horizons, and which is known under the name of the so-called strong cosmic censorship conjecture. And the idea is that generically irregular Cauchy horizons, as we have seen it in Kerr or also Reiser-Nordström, for all cosmological constants, they do not exist generically. And indeed, general relativity is deterministic in that sense. But of course, one has to make this conjecture a bit more precise. And the ideal conjecture which one would like to be true is the so-called Z0 formulation of strong cosmic censorship conjecture. So this says that for generic initial data for the Einstein equation, if the arising solution, then the arising solution is inextendable as a spacetime with continuous metric. So this means for Kerr that generically there should not be C-infinity extensions, but however, at the Cauchy horizon, if that thing exists, then hopefully your spacetime is not extendable as a C0 spacetime. And why is that? Why is Z0? Well, kind of this corresponds in a formal way to the fact that an observer approaching that boundary will then actually be determined uniquely to die and be torn apart by infinite tidal deformation, and that is actually also the scenario what happens in the Schwarzschild case. And I think throughout this conference we have also learned that a first problem to address before one can address the full Einstein equations is always to look at the toy model of the linear wave equation, or in the cosmological constant actually the conformal wave equation. And so the Z0 formulation has a linear analog, namely that solutions C to the conformal wave equation arising from generic initial data blow up an amplitude at the Cauchy horizon. And amplitude blow up now kind of is the linear analog of the continuous metric inextendability. But I already give you bad news, namely that the C0 formulation is false for the cosmological constant lambda equal to 0 and lambda positive. And this is a remarkable theorem now a couple of years ago by the Luke, who proved that all solutions converging settling down to Kerr are continuously extendable. And so that's already bad news for the case lambda equal to 0 and lambda positive. However, let me just briefly mention that I looked at a model which also includes massive matter together with Van der Mortel this year, and there the answer is not so clear, and it may be even that some version of C0 formulation of the strong cosmic censorship holds true, at least in that massive matter model. So what's the way out? Okay. Not all hope is lost. Maybe some weaker version of, if you want, determinism or predictability of the theory holds true, and that is the so-called H1 formulation of strong cosmic censorship, which is due to crystallo actually. And here we require that that for generic initial data, the Einstein equation, the arising solution is inextendable as a spacetime with continuous metric and square integrable Christoffel symbols. So it is actually easier to prove that conjecture than the previous one. And again, here we have a linear analog, which is that solution to the conformal wave equation, again, as before, arising from generic initial data have infinite local energy, so H1 log norm at the Cauchy horizon. So now, I already told you that indeed the C0 formulation is false for lambda equal to 0 and lambda positive. So what about the H1 formulation? And I have created this, this table. Okay, so what is known? Okay, I told you already that the C0 formulation is actually proven to be false for the fully nonlinear Einstein equations in the case of lambda equal to 0 and lambda positive. And also this result, which is the one here by the famous Luke, and apologize, all these people have worked in kind of completing this table, and apologize that I don't do justice now referencing each correctly, but anyway, but in any case, those two results, they were also preceded by those results essentially. On the nonlinear level, as okay, maybe natural, was preceded by the results on the wave equation. So what about the H1 formulation, which is, I told you, easier to prove, and it's actually known now that for the linear wave equation on lambda equal to 0 and lambda positive, both of them are proved to be true. For lambda positive, it's only, the H1 formulation is only partly true because actually the decay on the exterior is exponential, and this makes it even harder to prove. And okay, I don't want to go into details. But anyway, but what I will focus now is on the case of lambda negative, and that's the problem I've been looking at, and I will focus for the second half of the talk. So, in order to kind of get an instability, the strongest form of instability would be the Z0 formulation, which at the Cauchy horizon, one also has to look at the exterior. Unlike the exterior problem, which can be studied independently from the interior problem by the domain of dependence property has also take the exterior into account and very highly kind of, relies on what happens on the exterior. So on the exterior, on the lambda negative case, the solutions of the linear wave equation, they only take a 1 over log, and that is some similar phenomenon as we saw in Gabriele Benomio's talk due to a stable trapping phenomenon. So this means that maybe the hope is that maybe in the lambda negative case, actually the C0 formulation may be true, and that would be an attractive possibility if you like kind of determinism or predictability of the theory. And actually, as it will turn out, this 1 over log decay is high frequency phenomenon due to these quasi modes Gabriele talked about, and they will form an interesting resonance with some interior singularities. And actually, it turns out that the Kerr ADS case, connections to small devices and Diophantine approximation in number theory arise, and the resolution will depend crucially on the notion of genericity imposed. So, okay, let's however start with something expected first, namely with the H1 formulation. And actually, this should have been the first thing I should have done, namely that the linear H1 formulation is true for Isonostrum ADS. In some sense, that is maybe a bit, and also, okay, is true for Kerr ADS. That is kind of adapting the arguments. That is somewhat expected because the decay is even weaker than in these two. So the instability is larger. However, one has to note that log is not a lower bound. Actually, I mean, one can show that there's no better upper bound, but log is not a lower bound. Anyway, let's not go into details, but let's talk about the C0 formulation now. And this is the first problem I looked at, and despite kind of this low log decay, one has that the C0 formulation of the linear analog of the linear C0 of the strong linear the linear C0 formulation of strong cosmic censorship is false for Isonostrum ADS, and that was somewhat surprising because okay, one would have thought that the log really generates a larger instability. So this is false. But now, kind of, in my opinion, the most interesting case, the last 4 minutes, I'm going to talk about the Kerr ADS case. And there, as I already said before, and I'll say again, that the solution now depends on the Diophantine properties of the dimensionless mass and angular momentum m and a. So to state the theorem, I have to introduce to you the set of all possible Curry-Diaz parameters where one can sensibly study this problem. Namely, this set I will denote by script p. Okay, so now the theorem is the following, and that the linear C0 formulation of strong cosmic censorship is true for bare generic Curry-Diaz black holes. So what do I mean by this? By this I mean that, more precisely, generic, so scalar linear perturbation, so generic solutions of the conformal wave equation arising from generic initial data, blow up in amplitude, that's the analogous of the C0 formulation, at the Cauchy horizon. Now for a set of P blow up, which is a subset of all possible Curry-Diaz parameters, which has the following properties. Namely, it is a fractal set. P blow up is dense in P. P blow up is bare generic, so that is of second category if you prefer that terminology. However, P blow up is Lebesgue exceptional, it's a Lebesgue null set. And okay, to remember, okay, bare generic means that a set is the countable intersection of open and dense sets. Now, okay, the theorem now could be, okay, I mean, okay, but, right, so this theorem says that, okay, when only at a kind of very awkward subset of all parameters do I have this blow up. And moreover, that's still a work in progress, so I state this as a conjecture, but in some sense the proof gives very strong indications that this conjecture is true, namely that the linear C0 formulation of strong cosmic censorship is false for the Lebesgue generic Curry-Diaz black holes. More precisely, all linear scalar perturbations remain bounded at the Cauchy horizon for a set P bounded of dimensionless black hole parameters with the following properties. And now, of course, it has to be complementary. Well, it's the complement of a fractal set. So, I mean, fractals are, I mean, if you're fractal, then the complement is not necessarily a fractal, according to various definitions of what you mean by a fractal. In any case, it is dense. Previously, the other set was also dense. It is Lebesgue generic. It has to be. The other set was a full Lebesgue measure. And it is bare exceptional. So it's the union of nowhere dense sets. Yeah. Right. So to summarize, now I was very quick. Okay, I didn't want to say this. Okay, now to summarize, in some, so the current state, in some sense, so now this theorem now also fill out, in some sense, the state of the art of the strong cosmic censorship conjecture for the linear wave equation. For the cases lambda negative. And in some sense, what I find the most interesting case is really that in the Curry-Diaz case, one has this intricate resonance phenomena, which actually kind of gives then new connections to small divisive problems, as one knows it maybe from KAM theory. And truly these Diophantine approximation plays a crucial role in the proof, and this is respected in the fact that indeed for bare generic and for Lebesgue generic sets one expects a different behavior. A final comment in the last 30 seconds I have is that this is open. The H1 proving any strong cosmic censorship conjecture is quite open because one has to prove it for generic set in the modular space of all initial data. So let's say even this is very open, but this is even very, very open. Because to address kind of the nonlinear dynamics in the strong cosmic censorship in the asymptote, the ADS case, and here I only speak about the Dirichlet boundary conditions, apologize if I didn't say this earlier, then or reflecting boundary conditions, then we really, I mean, the exterior stability is very unclear, and Gabriele said, okay, he thinks it's unstable. I wouldn't go so far, and this is, so that's why I say this is very, very open. And well, thank you very much for your attention.
Thank you very much. Questions?
Thanks for the talk, for the nice talk. Can you quickly say for 1 sec more about the work you did with Maxime? Like, what is the model you studied? What is your result?
The result is that so we we look at the Einstein spherical symmetry coupled to a charged massive scalar field, and there the exterior is only at the inverse, is only v to the minus some power which is smaller than 1 on the event horizon. That's the expected behavior in physics literature. This hasn't been shown. So we pose those data on the event horizon which are not integrable, and this is inside the integrable. If you want to prove C0 C0 formulation is false, you need that the event horizon is integrable if you want to use decay. And yeah, and we pose slowly decaying data on the event horizon, and then it's actually not so clear. Yeah. I mean, there are data. Yeah. I can tell you more about this in terms of the time. Yeah.
Does anything actually change if you go from conformal wave equation to?
No, and indeed, as always, the conformal thing is just to, in some sense, I mean, I have to kind of intricately construct those quasi-modes at the resonant frequencies, and it's in some sense this theory is much better if you have actually regularity at infinity. But I expect it to be also true for the whole range of the Neumann case and the Dirichlet case, yeah.
Okay, let's thank Christoph again. Thanks for your talk. All right, and there's only one more talk left, which will be by Simran Arora from the Birla Institute of Technology and Science, Pilani. And the title of the talk is Effective Equation of State in Modified Gravity and Observational Constraints. Please.
Thank you so much, everyone. And am I audible?
Yeah, we hear you.
Okay, thank you. So first of all, I would like to thank the organizers for giving such a great opportunity. And I should share my presentation. So today I will be presenting on a topic, effective equation of state in modified gravity and observational constraints. So basically this is the outline. So I will be giving a brief introduction about the cosmological view, the modified gravity FRT, what are the observational constraints we are applying on, and I will be explaining the behavior of cosmological parameters such as deceleration parameter, equation of state parameter, state finder diagnostics, energy conditions. So as we know that the recent observational advances in cosmology have provided.
I can't see your slides.
Oh,
yeah.
Wait.
That looks better.
Is it visible now?
Yeah, we see it now.
Okay, sir. Yeah. So today's topic is effective equation of state in modified gravity and observational constraints. So these are the outlines which I have described. So as we know that recent observational advances in cosmology have provided strong evidence that recently our universe entered in an accelerated expansion phase. So as we all know that general relativity is the most successful theory of relativity, but there are some observations that limit the general relativity, which we all know as general relativity has some issues like cosmological constant problem or fine-tuning problem. So in 1998, two scientific groups led by Rees and Perlmutter studied distance type Ia supernova and proved that universe is accelerating. So what is this cause of expansion? So several models hypothesize the existence of a mysterious component called dark energy and could persist in anti-gravity feature of speeding up the universe expansion. So the simple model which was proposed was cosmological constant. which plays the role of dark energy. That was a fluid with constant energy density and high negative pressure. So that what I have mentioned, that lambda CDM model has some issues: cosmological coincidence problem or fine-tuning problem. So after that, there many people propose some dynamical models, which includes scalar field, quiescence, quintessence, bulk viscosity, Chaplin gas. So up to now, the nature of dark energy is still unclear. So how we can explain the nature of dark energy by some other means? So another mean is we can modify the Einstein theory of gravity, like a modified theory of gravity. How we modify the gravity is like we introduce an arbitrary function in a gravitational action, like this Fr. This is an arbitrary function of precise scalar R, and then we will try to frame a model and study the nature of dark energy. After this journal extension of CHAR, there was another extension which is known as FRT gravity, where F is an arbitrary function of precise scalar R and T, the trace of energy momentum tensor. So we will be studying the dark energy using some functional, by assuming some functional form of FRT gravity. So depending on the meta source for each choice of F, we can obtain several theoretical models corresponding to different matter models. So there are three forms of FRT gravity. First one is R plus 2FT. Second is F1R plus F2T. Third is F1R plus F2R F3T. So mainly in this work, we will be focusing on the first function form. So in FRT gravity, the cosmic acceleration may result not only from a geometrical contribute to the total cosmic energy density, but also in the matter content. So here this T, this represents the matter content of the universe. So after that, what we will be considering is the viscosity effect, which can be concerned with the evolution of universe. So along with the FRT gravity, we will be studying the viscosity effect for the evolution. So what kind of cosmic viscosity element can play in helping the specific dark energy? So basically, there are two viscosity coefficients. One is the shear viscosity and second is the bulk viscosity. So shear viscosity, which is related to the velocity gradients in the fluid, and considering the universe also described by the homogeneous and isotropic, it can be omitted. But in this work, we will be focusing on bulk viscosity coefficient. So E comes up in the standard expression for relativistic viscosity in 1940. So the concept of bulk viscosity was later explored in the form of inflation barrier. And how this bulk viscosity works, like in a cosmic fluid, it can occur when the fluid expands faster than a system has to recover its local thermodynamic equilibrium. So active pressure which emerges, restoring the system to its thermal stability. This effective pressure can be regarded as an indicator of bulk viscosity. So the introduction of viscosity into cosmology has been investigated from different viewpoints, such as unified dark matter, the cosmic singularity, and the dark energy models. So there are some works in literature which studies the role of dark energy with the viscous fluids. So Cagnon and Lescordius presented the role of dark energy in explaining the acceleration of the universe and linear perturbations of the model. Brevet also introduced bulk viscosity in the formalism of modified gravity. Again, Wilson and his group invested bulk viscosity, decaying dark matter, and cosmic acceleration. Singh and Kumar introduced the bulk viscosity in the formalism of modified FRT gravity and studied the expansion of the universe. So again, there are two groups which studied the viscosity effect in different modified gravity, which is FT gravity. It is an extension of, further extension of modified gravities. So in this work, we'll be studying a geometrical frame model with the bulk viscosity in modified FRT gravity theory and try to constrain the model parameters using Hubble datasets and supernova datasets. These two datasets, they are observationally present in our literature. So overview of FRT gravity is the most general action which I have described previously is this, where FRT is an arbitrary function of R and T. So we try to do the variation of this action with respect to metric tensor, which gives the gravitational field equation. And then we try to consider and assume the FLRW matrix in the flat space geometry, where AT, it represents the cosmic scale vector. After that, we the 4-component velocity is like 1, 0, 0, 0 in comoving coordinates, and we try to introduce the bulk viscosity coefficient in the energy momentum tensor, which reads like this, where this P bar denotes the effective pressure that is due to the bulk viscosity coefficient. And we assumed the functional form of FRT as R plus 2 ft, and we try to figure out the field equations as equation 10 and 11. So from these two equations, we try to find a solution in terms of Hubble parameter. So from equation 10 and 11, we solve these equations, but solving this equation leads to some problem because it has more unknowns than number of equations. So what we do is, to get an exact solution, we need more physically viable equation, and we consider an equation of state in this form. So what is the motivation behind this form is discussed next slide. We compare with the bulk viscosity form, which we consider in this paper is xi naught plus xi1 a dot by a plus xi2 a double dot by a dot. These two equations, that becomes equivalent, and we try to find these coefficients in terms of this effective EOS we have considered. So that was the motivation behind this. These two equations, that becomes equivalent in these coefficients can be expressed in terms of each other. So from these two, all these equations, we can find the explicit form of energy density and Hubble parameter in terms of cosmic time t. But to study the observational constraints, we need all the cosmological parameters in terms of redshift z. So we try to convert these cosmological parameters in terms of redshift. So from this Hubble parameter, we can find easily the scale factor, where, however, this h, this is given by a dot by a, and k4 is a constant of integration. Again, with the help of scale factor, we can find the deceleration parameter q. So yes, which I have mentioned that we have to convert all these parameters in terms of redshift z. We can use this relation to convert them into z, and we got these relations as equation 21 and 22. So these two equations, they contain unknown parameters as k4 and k2. So we try to constrain these two parameters from some observational data sets. So here we have considered two observational data sets. One is the Hubble data sets, which contain 57 points, and second is the supernova data set, which contains 580 points. So this is the error bar plot of a model considered. This is the plot of Hubble parameter, in which this red line depicts our model, and this black dotted line represents the lambda CDM model. And this dots represent the errors or points of the Hubble data sets. Similarly, mu z, it represents, red line depicts our model, and black dotted represents the lambda CDM model. So it shows that our model fits the observational data sets. So what now constrain these two unknown K2 and K4, we use this chi-square function, which we used for two data sets, HZ and supernova data sets, and we used the H naught value as 67.66 kilometer per second per megaparsec, which we have considered from the recent Planck 2018 data. This is the formula for chi-square for supernovae data sets, and we got these two contours and the best fit value of two unknown parameters K2 and K4. So we got the value as K2 as 3.0 and K4 as minus 0.389 and minus 0.43374 according to the respective data sets we have considered. Next comes the deceleration parameter. So in a new cosmological model, the Hubble constant H0 and deceleration parameter Q that play an essential role in describing the nature of evolution of the universe. So H0 represents the expansion rate, while this Q represents whether the universe is in accelerating or decelerating phase. So we have plotted the behavior of density, which is positive, and the behavior of deceleration parameter, which has a transition from positive to negative state. So as indicated, Q negative represents the accelerating phase of the universe. And so we can say at present Z equal to 0, the universe is in an accelerating phase. So according to the data on the constraint values of unknown parameters K2 and K4, we obtained the present value of deceleration parameter minus 0.77 and minus 0.68 with two different values of K4 from the two datasets HZ and supernovae. So this indicates that universe exhibits a transition from early deceleration to current acceleration. Next cosmological parameter is an equation of state parameter, which represents the relation between the pressure and the energy density. So according to the different values of the EOS parameter, there are different phases of the universe we can see. For omega equal to 1/3, we have a phase as radiation, omega equal to 0 as dust, omega equals to 1 as stiff matter. When omega lies between -1 to 0, it behaves like quintessence, -1 behaves like a lambda CDM model, and +1 as a parameter error. So according to our model, the behavior of equation of state parameter behaves in the similar fashion as the deceleration parameter. It shows the transition from positive to negative, and omega lies between 0 and -1 at present value. So it indicates that the universe is showing a quintessence behavior. Next comes the state finder diagnostics. So we have used the state finder diagnostic, which was introduced by Sahani et al. In 2003. And the state finder is a model independent geometric diagnostic tool that allows us to characterize the properties of dark energy. So the form of R and S parameters are represented in equation 26, where this A represents a scale vector, Q represents the deceleration parameter. So this is the behavior according to our model, this SR plot and QR plot. This SR plot, the point 0.01, it represents the cosmological lambda CDM model. Sorry. So we can see that RS parameter, it behaves like it is resembling the lambda CDM in future and ultimately freezing to it. So the trajectories in SR plane, they are lying in the Chaplin gas model of the dark energy, which represents the phase at R greater than 1 and S less than 0. Similarly, in QR plane, this point R equals to 1 and Q equals to -1 represents the de Sitter phase, with the steady state model. And it also lies in the Chaplin gas phase. Similarly, we have obtained the S0, R0 values according to the two different data sets. And it can be seen that the model is distinguishably different from the lambda CDM model, but might reach to the lambda CDM in future. So this is the, I have done this. So energy conditions now. So energy conditions have a great adequacy in general relativity, which consider the singularity problems of space-time, and basically explains the behavior of null space like time life or light like geodesics. And it provides us some flexibility to analyze certain ideas about the nature of cosmological geometries and some relations that stress energy momentum must satisfy to make energy density positive. So basically we have four energy conditions. First is strong energy condition, which represents rho plus 3p greater than 0. Dominant energy condition, weak energy condition, and null energy condition. So we try to figure out these the behavior of these four energy conditions. And basically the violation of strong energy condition represents the acceleration. So the energy conditions behavior, and we can easily see that null energy condition, dominant energy condition, they are validating their conditions, but the strong energy condition at some point of the redshift does not validate its condition. So it violates the condition, and violation of strong energy condition represents the accelerated phase. So what we have concluded in this work is we have studied a cosmological model in which we have discussed the phenomena of cosmic acceleration with the viscous fluid. We have considered an effective equation of state which describes the late time acceleration of the universe without introducing a cosmological constant. We have also observed the deceleration parameter, which shows a signature flip from early deceleration to present acceleration at the transition ZT as 0.84 and 0.61 for two different data sets, HZ and supernovae. Further, we have also mentioned the behavior of EOS parameter, which is again showing a transition from again the positive to negative regime, and it can be seen that incorporation of bulk viscous pressure might play a role in studying the nature of dark energy or an accelerated expansion. Also, at last, we examined the energy conditions as well as state finder parameters to study the different or to differentiate between the model we have considered and the lambda CDM model. So at last, we can say that the present effective viscosity model may be considered as an alternative candidate to explain the late time accelerated expansion of the universe. Thank you.
Thank you very much. Are there questions or comments from the audience? If not, we thank Simran again, and maybe we can thank all the speakers of tonight's session again. Thank you very much all for contributing.